Thank you all for joining this week's colloquium. So today we have a very special guest, Elaine Lee, who's a professor of physics at UT Austin. So Elaine received her Ph.D. from the University of Michigan in 2003, and then worked as a postdoc at JILA up until 2007, where she joined UT Austin as a professor. So since her time at UT Austin, where she established a research group, she's made many seminal contributions to several different research areas. So including but not limited to spin dynamics in magnetic materials, plasmonics, and most recently, sort of the fundamental optical properties of van der Waals semiconductors and magnetic materials and their heterostructures. She's received a lot of awards, way too many to list here, but a few of them include the Presidential Early Career Award and also a Sloan Fellowship. And she's also a fellow of the American Physical Society and OPTICA. So it's truly an honor to have you here. And
thank you very much.
Looking forward to your talk.
Thank you for the invitation, Kyle. And it's great to be here to see some old friends. Jason and I were at JILA together. We even negotiated the optical table purchase because we started our assistant professor position at the same year. Anyway, so I'm going to tell you a little bit about optical property of semiconductors, and particularly Moiré superlattice. This college, in fact, has a lot of renowned scientists working on semiconductor optical properties. I learned basics from actually a book written by someone who recently retired, Peyton-Barron, Professor Peyton-Barron. I know that Kyle is taking over his last place. So anyway, so I've had a lot of ties with this place. And I just want to say that I know that you all come from a pretty broad background. I know I have a few super experts in the room, but also have a lot of young students probably are not looking at semiconductor optical properties. So just feel free to interrupt me and ask a question. I don't need to talk to myself. I know what I'm talking about, just so we can stop anytime. Okay, so first of all, most importantly, let me acknowledge who did the work. This is a picture of my group before the pandemic. It's really old. Have a lot of wonderful collaborators at UT Austin, including two theorists, Alan McDonald, Aslan Khalaf, who unfortunately was recruited by Harvard. It's hard to compete with them. And also, I'll be showing some results from my colleague, Kanshi, who does STM work on these materials. And then a lot of work recently we've done using scanning probe. We're actually collaborating with a group in Texas State, 40 minutes away from us. Students, early students who work on Moiré physics in my group have already moved on to better and greater things. Junho is starting his own group in Korea. And a lot of work I'm presenting today were done by two graduate students. This is our theory collaborator from Aslan's group. Okay, so let me explain this line of research go based on the ideas of how do we engineer properties of material by confining the electron motions. So naturally, you have electron can move in all three dimensions in the solids. If you find a way to confine their motion in the two-dimensional plane, you made a quantum well. In fact, a lot of us have, all of us have smartphone. The highest performance transistors are built with quantum well. If you can further confine the electron motion to a one-dimensional wire, you have a quantum wire, then the ultimate limit is confined electron motion in all three dimensions, and you have a quantum dot. So this is a way to engineer properties, change the possible energy state electron can occupy in a material. From a dimension point of view, you can change many properties of the material, including how they emit color, the light emission color of the material, and also the statistics of the emitted color, of emitted light. So in quantum material, size matter. If you have a rubber ball, you make it smaller, still a rubber ball. But this is an iconic picture for people who make nanocrystals. And what they have done is to basically put droplets of semiconductor in a solution. The solution, that reaction happens very fast. Over 10 minutes, depends on the size of the quantum dot, the emission color will change from red to blue. This is, you're confining the electron motions. And let me ask a question to the students in the audience. Which one of these colors have smaller quantum dot? Blue, because we're, quantum mechanics 101, if you confine the electron motion tighter, the energy spacing gets bigger, the color becomes blue. Interestingly, this work has been going on for a long time. It was recognized by the Chemistry Nobel Prize last year. And these fellows were recognized for their contribution to how to create quantum dots. And there's a basically simple article always written by the committee to introduce the contribution of these distinguished scientists. They literally had an article titled, "They Added Color to Nanotechnology." Of course, it's not just about adding color to nanotechnology. These quantum dots find many applications, including in TV screens. You can see quantum dot TV, they're there. Okay, another Nobel Prize in physics about 15 years ago now was given to these two gentlemen. What they have done is to learn how to exfoliate a single layer of material using Scotch tape. It seems really simple. And their paper published in PNAS in 2005 actually identified many material that you can create. Some of them graphite, graphene, or semi-metal. Others in this class of materials called transition metal dicogenite, which I'm going to focus on today, are semiconductor. Some are superconductors. And what they've done is really find an easy way to create two-dimensional material in the ultimate limit with either a single layer of atom or unit cell thickness. So I think at the time there were a lot of debate, do these folks deserve Nobel Prize? And it's very rapid since they made the discovery. 5 years later, they got a Nobel Prize. Chemists were upset. They say, we know how to do this many years ago. But I would say certainly today, what they have started represent a very active era in condensed matter physics and material science. The main material I'm going to focus on today is the semiconductors. And they have 3 atomic layers with a transition metal in the middle and chalcogen atom on both sides. If you look at this material top down, you see honeycomb lattice with the AB lattice occupied by different atoms. And this MOS2 monolayer indeed was created, isolated quite some time ago by this scientist in Canada and published in a decent journal. But at that time, people were not studying their optical property, which is, what I'm going to talk about today. So you can create them using exfoliation method coming from a bulk crystal, thin them down to monolayer, bilayer, whatever thickness you want to create. You can look at optical contrast, and people have learned how to grow them using chemical vapor deposition. I think Intel actually had one of the largest TMD grown. They're very proud of it. So certainly companies are looking into these semiconductors. They have the wonderful property you can terminate the material thickness exactly 1 layer at a time. And there's many variety of them, so you can look for many interesting things. One of the things I'm going to focus on is their optical properties. So this is one of the early paper. The green light represent looking at photoluminescence coming from bilayer of this MOS2. And the red light is actually a single layer. Between bilayer and single layer, light emission become 100 times more efficient. So what happened there? So this peak is what we call the exciton peak. And what's an exciton? Okay. So in semiconductor, there are 2 important classes: direct gap semiconductor, indirect gap semiconductor. It just means whether the top of the valence band is aligned with the bottom in the conduction band in the quasi-momentum space. Direct semiconductor, whenever you're interacting with light carries very little momentum compared to the whole range of the Brillouin zone in the solids. And so therefore, anytime when you involve light matter interaction, it's typically a vertical transition. And if you have an indirect semiconductor, for example, silicon, and you're not going to be able to make a transition from the bottom of the top of the valence band to the bottom of the conduction band directly. So there's some other process need to be involved to satisfy the momentum conservation. But silicon, the most important semiconductor, of course, are used as detectors all the time. We still use them as detectors, but their efficiency will be better if they were made into direct gas semiconductor. So what happened is actually between 2-layer and the single layer, the band structure made a transition from an indirect semiconductor to a direct semiconductor. And that's why light emission becomes 100 times more efficient in a monolayer than a bilayer. So that is really a dramatic example of quantum engineering, thinning down the material, changing the possible energy state electron can occupy, changing the band structure, making the material become from an inefficient light emitter to efficient light emitter. Right? It's following a long line of strategy using quantum confinement to change property of materials. Right? So this is a wonderful example of being able to do that. Okay, so another thing that's somewhat different is this exciton resonance that I show you, this peak emits, right? In gallium arsenide, in good old gallium arsenide, that happened in the center of the Brillouin zone. But in this material, these transitions happen at the boundary of the Brillouin zone. This is the hexagonal Brillouin zone, and these transitions for the excitons happen at two valleys, K and a K prime valley. They are inequivalent. They're related to each other by what we like to say time reversal symmetry. What that really means is the spin state occupy the bottom, the top of the conduction band in two valleys are flipped. So as a result, the light emitted from a transition in one valley to the other valley are reversed in the photon chirality. So if you want to excite a transition in K valley, you just use sigma plus light. If you want to excite a transition in sigma, K prime valley, you reverse the helicity of the light. So this is there's a nice relation between chirality of the photon emission to where they are in the valley. Valley itself, it just means minimal or maximal in the band structure. Every material has valleys, but typically you cannot controllably occupy or confine the response to one valley. This material has the unique property. You can actually choose to populate one valley or the other valley, or you have light emission that are sigma plus, it comes from one valley to the other. So it almost like it gives you another binary degrees of freedom to encode information. So there are people called this valleytronics, is based on this idea. There are two, this valley index, binary, have different property that allow you to encode information. Okay, so in these materials, we have a zoo of quasi-particles. What I mean by quasi-particles, basically either a bound electron hole pair, that's an exciton. I show you that excitation of electron from valence band to conduction band. What you actually left behind is a hole. Hole is positively charged, and there's a Coulomb attraction between the two that give you this bound state called exciton. And the binding energy is surprisingly large. And in gallium arsenide, you have exciton, but nobody really care about them at room temperature in devices because the binding energy there is about 5 to 6 MeV. And thermal energy, if you take kBT, that's 25 MeV for room temperature. So exciton is not stable at room temperature in gallium arsenide devices. But in these monolayers, because they're so thin, the Coulomb field that bounds the electron hole pair actually permeates outside the layer that enhances the binding energy to something like 200 to 400 MeV. So it's a quasi-particle that are stable at room temperature. You cannot ignore them anymore. So you have to deal with them. And this is a exciton bound electron hole pair. Here's a trion. Basically, an exciton bound with an extra charge, either electron or hole, strangely, they're energetically more stable than exciton. This trion transition appear at lower energy than exciton transition. You can also have what's called the biexciton, two exciton bound together, and they're also energetically stable. All of these particles has binding energy about 10 to 100 times larger than the traditional semiconductor quantum Waals and quantum dot. So that makes these systems really interesting to study, make these quasi-particles very important to study for all sorts of optical electronic devices. In the realm of quantum information science, these particles have different roles. For example, a single exciton, if you can isolate a single exciton, they will emit photon one at a time, so they become solid state single photon emitters. If you have a single trion, they serve as a way to entangle spin and photon in the material. And biexciton becomes a source of entangled photon pair generations. So this topic have all been studied in the good old gallium arsenide, indium gallium arsenide, semiconductor quantum well or quantum dots. But now they're being restudied in some ways in these materials because they have a very stable, large binding energy. They become stable at room temperature. Okay? And when you dope the material, now you shine light on to create electron hole pair, you actually need to worry about whether this electron hole pair are interacting with the entire Fermi sea, then you have actually more complicated situation. But I'll skip that for the purpose of this talk. So that is to say, all of these transitions will lead to a prominent resonance in light emission spectrons or absorption spectrum, and they are stable at room temperature. So this is I'm going to tell you how these transitions are getting modified when I build an even more complicated structure. So this is the first part of my introduction. I want to pause and see if there's any question from the audience. Everybody is with me? You heard of this many times? Okay, let me go on. But now you can build a Moiré superlattice by simply take two layers. And because the layers have weak van der Waals force between them, you can now rotate them. You know, when you're, again, if you're growing gallium arsenide based quantum well, each layer had to be epitaxially matched. But these materials don't have that constraint. You can just choose to twist the angle. And now you can see that I have this superlattice developed in the plane. The larger the angle, the smaller the superlattice. What are they? They're actually quantum dots. More precisely, they're quantum pancake, right? You have the vertical dimension, very strong confinement coming from the single layer material. Now you twist, you create these little boxes, and they can confine individual electron, individual hole, or electron hole pair. So they are basically, I'm evolving from a two-dimensional system to a zero-dimensional system, an array of them too. So we'll see, how do I tell this is actually, I do have what I imagine that's happening. Okay, so now I'm going to the main part of my talk. I'm going to tell you about Moiré potential, how energy structures are changed in the Moiré system, different type of excitons and selection rules. And how do I know these excitons has anything to do with the Moiré? I'll look for property of these excitons that are tunable by the twist angle. I show you the energy and the lifetime of these excitons are changed by the twist angle. But what I'm really excited to share, these are somewhat old results, a couple years old, but I'm really excited to share with you a new way of generating Moiré potentials that I hope can impose these periodic potential in a much wider range of materials. Okay, so this is what I really would love to focus on, tell you more about. These are more recent results, some unpublished. Okay, so first of all, let me use my colleagues' results that they do STM measurement. You have experts here at Arizona doing scanning tunneling microscopy measurement. What these techniques can offer are atomic resolution. They can measure local band structure. In this particular cases, they're studying these combination of material. They're chemically grown. They're not stacked together. Only physicists stack these things together because we don't know how to do chemistry, okay? But people can grow them, on wafer size. And, when you grow them, these two materials have different chalcogenide atoms. Because of that, the lattice constant differ from each other by a few percent. When they grow energetically, they tend to align the crystal axes because that lowers the energy. But even when the crystal axes are aligned, because their lattice constant is different, you can see when I shift around, the top layer and bottom layer atoms are gradually shifting. Okay? So this is give me the Moiré superlattice. I can look at one location that's A stacking. I'm just going to use the terminology. It means the top hexagonal is perfectly on top of the bottom hexagonal. You move over by a few unit cell, and now one of the atoms stick out in the top layer hexagonal center. So then you will have these few high symmetry points that maintain the rotational, threefold rotational symmetry. These high symmetry points tend to be the energy minimals in the Moiré potentials, where a lot of things are happening. So this is a picture of topology. The layer spacing are actually gradually changing. But you can also, if you do a measurement like the electron densities, this is also approximate true. So when you start to inject electron into the semiconductor, they're going to find their energy local minimum. So they're going to form this checkerboard patterns, right? So our goal is to eventually put one electron at one of these sites or put one electron hole pair at one of these sites. Now I get an array of individual quantum systems, right? Hopefully, if I learn how to control them, I can make some magic happen. Okay, so these are Moiré pattern forms. You can measure them with different tools. This is STM. This is STEM. Simulation experiment. Everybody knows except that these Moiré superlattices exist. And now I can measure their local band structure. Let me just focus on this. So these are the few high symmetry points, right, that with slightly different atomic alignment. And this is measurement experiments. So you can see from one location to the other location, the local band gap changes by 200 MeV. That's quite sizable compared to total band gap. And here's a calculation. The calculation is off. It's because fundamentally first principle calculation has a trouble defining what's a band gap. But importantly is the trend at different local stacking, the experiments and the calculation agree with each other. So we know their band gap modulation, and that's where you would find electron preferably sits at one place versus the other place. So there's a wonderful material, you twist them, however you know how to do it, grow them or mechanically stack and twist them, and they just give you this checkerboard modulation. With the size, any size you name it, I can control the twist angle, I can change the size. Right? So let's look at their optical properties. I've been talking about excitons. They're bound electron hole pairs, both in the energy band structure, but also in real space. The size of these electron hole pairs, two-body problem, there's a movie three-body problem, right? No, we don't deal with that. We deal with two-body problems, okay? Two-body problems, you can always restructure them to discuss the center mass wave function and the relative wave function. Sometimes I would say one state and higher excited state, I meant the relative wave function are changing, electron hole are changing their distance. Other times I say excitons are confined. What I mean is the center mass wave function is localized. Okay, so there's two things you need to worry about. So there are different ways to form electron hole pairs. They can be in the same layer or they can in an opposite layer or two different layers. So this, I call them intra-layer exciton. This interlayer exciton. Their properties are very different because the interlayer excitons, they're separated further apart. They have much longer lifetime. The intralayer exciton, it's amazing. You take a single layer, you shine light on it, 5 to 8% of light resonant with the exciton energy gets absorbed. So they absorb light very strongly, just a single layer. By virtue of that very strong light matter interaction, they have a very fast radiated decay on the order of a picosecond, right? They go very fast, and these folks go much slower. Starting with a nanosecond, as I can show you, they can be much longer, depends on how you control the twist angle. And also one thing that's more, I've told you about the atomic alignment. I know this picture makes me dizzy too. Let me just say there's 3 local stacking where you are likely to find the excitons or electrons and sit at these particular locations. And I told you about the valleys, right? K and K prime valley in monolayers, and they're accessible with sigma plus or sigma minus light. So now I'm just going to talk to you about one valley. The other valley exists, always give you the time reversal copy. So let me keep track of one valley. It turns out if I can manage to create an electron hole pair at one of these 3 locations, they follow different selection rules. So now I have a material, not only I have energy modulation periodically with a period anywhere between a few nanometer to a micron, you can control with a twist angle. The energy modulation can be on the order of 200 MeV, shown by the STM measurement. There's also a polarization pattern for light emissions. If I were to create the exciton localized at these locations, I would actually have this polarization emission patterns for one valley, and the opposite valley will reverse the selection rules. Okay, so you're like at this point, I was getting a little dizzy over this. This is pretty complicated, right? And another thing to keep in mind, the period of this is 10 nanometer, 20 nanometer. When I study them with optics, I have a micron size beam. I'm exciting hundreds or maybe 1,000 of them simultaneously. It's actually very difficult to relate my optical spectroscopy to this local pattern. Okay, so it took us a long time, and this is an early work. I don't remember if John is involved in that, but just to articulate where the intra-layer excitons are, where the inter-layer excitons are. Interlayer exciton was like lower energy, partially because of type 2 band alignment in this material. That's a minor detail for today's talk. But we also, another thing that people learn is to actually encapsulate them in HBN. HBN is this high gap insulator with 6 eV gap. They're transparent. The sample are ugly if you exfoliate and stack them. So this is where they are. And then we had this result for a couple of years. We don't know what they are. We thought maybe they're bubbles, that maybe sample are just inhomogeneous. And that it takes a very dedicated students make a dozen of them. And then we slowly to notice some trend. So here is a spectrum taken for interlayer exciton with 1 degree twist angle. Here is another heterostructure, 2-layer structure made of 2 degree twist angle. Okay, now I take these spectrum on many different locations on the sample. Sure enough, there's some inhomogeneities. The energy is fluctuate a little bit, but the energy spacing seemed to be getting larger with a 2 degree twist angle. Again, for simple quantum mechanics 101, larger twist angle, smaller quantum pancake, bigger the energy spacing. So that's the first indication. Maybe I have something that's related to this quantum pancake. And then the next thing is we got lucky with this sample that in photoluminescence, we're able to see exciton with alternating preferred polarization, circular polarization. Remember, I told you there's a spatial pattern of polarization changes. So maybe this is another hint. Perhaps they're related to these Moiré systems. We still cannot be sure. It turns out there's another explanation why you can have this alternating selection rule. These Moiré potential are kind of deep. So if you solve a square Waals problem in quantum mechanics, you can have not only the ground state, but excited state. So it turns out these ground state excited states have different center mass wave functions, and they also follow different selection rules. So there are really multiple ways that you can actually have multiple exciton resonance, follow different selection rule. We chose this picture in our published work, partially because we see the higher energy peaks were disappearing faster with temperature. They have shorter lifetime that just indicate maybe they're higher energy states. So that's the picture we picked. And let me just say, even today, there are alternative pictures being proposed to explain those multiple peaks. And people either look at different combination of material. It's still a matter that's under debate. You need to use more sophisticated tool to really tease out a problem than what I've showed you. Okay, we did our best, based on our understanding, gave an interpretation, and that interpretation could very well evolve as we look at them with more sophisticated tools. Okay. Another thing that's interesting is the lifetime of these transitions are changing with twist angle. You remember there were multiple peaks, right? When I look at different energy peaks, I find high energy peaks decay faster. That's one of our reasons to believe they're higher excited states. And also, as you twist the angle, 1, 2, 3, the lifetime was getting much longer with the twist angle. What's going on? There's a simple explanation. When you twist the layers in real space, you're actually also twisting their Brillouin zone in the momentum space. Now, these transitions happen at the KK point, the corner of the Brillouin zone, right? But when I twist, I shift the conduction band away from the valence band. Now it becomes a little bit indirect. I started by saying direct semiconductor, direct gap semiconductor, indirect gap semiconductor would be very different. So I made these things a little bit indirect transition. And that's why lifetime was getting longer. So it needs a phonon, sometimes needs a phonon involvement to make that process happen. So I feel like if I just have a spectrum, it's hard for me to call those excitons Moiré excitons. I must show you some property that changes with the twist angle, okay? So this picture does not even require Moiré. It just requires heterostructure, but shifted band structure in momentum space to have different lifetime. Anyway, so you can see many property of these Moiré emitters are tunable, right? So let me repeat the take-home message. I've shown you different type of excitons, intralayer, interlayer excitons. I showed you their selection rule is far more complex than a monolayer. I don't have that sigma plus to K value, sigma minus to K value anymore. I may have a spatial pattern of selection rules. And the exciton properties, their energies, lifetime, and also the diffusion behavior can change by the twist angle. I skip the diffusion. I don't have enough time to tell you about that. So the problem is all of these properties change simultaneously. If I want an array of quantum emitters, I actually don't want long lifetime. When you have a long lifetime, there's non-radiated decay process that compete with the radiated decay process. I actually don't want them to change simultaneously. So this has always bothered me. I want to tune these properties independently. Can I do that? The twisted TMD is wonderful, but also has its own limitations. Too many things are changing simultaneously when I twist the angle between the two layers. So I'll again stop here because I'm going to start my next section. Before I do that, I want to see if you have any questions for me on this part. Yes.
Observe phenomena like superradiance and subradiance with these emitters?
Absolutely, I wanted to do that. We have not succeeded. You know, the superradiance, basically you require collective light emissions. To begin with, you actually want the dipole to be all aligned. You know, of course, people tried that with molecules, with quantum dots. It was hard to orient the dipoles. This does seem to have a better chance to do it, right? Still, we have not succeeded. I had an NSF proposal, you know, 2 years. I need to think, you know, we designed a matter surface, try to kind of coerce the collective light emission. It is too sensitive, the matter surface. If you move the emitter slightly, it changes the things very sensitively. So we're not able to see that collective emission yet. But it's one of the things a lot of people would ask. So now you have an array, well-aligned dipoles, can you just let them emit collectively, right? We have not gotten there. So if you want to work on it, great, go for it. We're not there.
You use DFT to calculate band structure to use the.
That's what that was what was used. You know, DFT, you can do atomic level calculation. That's what people do. They just calculate very local bands, take an atom on the top and atom on the bottom. Calculating the entire supercell was very difficult. Calculating excited state was even harder. You know, one group mastered it. You know, maybe it won't be a surprise, Stephen Lewis group at the Berkeley, right? They've learned, you know, a young, really, Mitt-Nike is the person who drove that effort. So they've learned how to do it. So they can now quite confidently predict excited state in the system, explain, you know, variety of reasons why the exciton isn't so simple as I pictured for you so far. There's a lot more complexity. What I showed you are basically understanding around 2020, where 3 years later, there are many tools applied. We have more advanced understanding of these excited states now. Yeah.
These are dominated by many body effects, in addition to these single particle interactions. And I was just wondering if people were routinely doing DFT kind of calculations to.
Right.
to
You
construct.
know, I think calculating exciton itself is a specialty, as you alluded to. It's not a single particle calculation. So of course, the DIT folks has, you know, beta-salpeter equation, GW naught, the variety of method they developed to handle that. Calculating Moiré is a challenge, but they're making a lot of progress there as well. Any other questions? Yes, please.
Yes, early on you mentioned bi-excitons, which can emit photon pairs,
Yes,
while excitons is a single photon.
yes.
Regarding of lifetimes, which ones?
The biexciton, it's almost twice as faster than exciton because they have two channels to decay. I'm not able to see single photon emissions or entangled photon emission from these systems yet. It's because I cannot isolate a single Moiré supercell. I need to find a way to harvest emission from a single supercell. Some of you may have worked on plasmonic kind of system. Is one of the natural thing to ask, can you use a plasmonic antenna to isolate a single emitter, right? Again, we're trying that direction, wasn't so successful so far. Isolating individual supercell is difficult, right? So we haven't seen a single photon emission from these Moiré supercell. But all very good questions and good directions to continue. Other questions? Yes, please.
When you were talking about the properties of rotating by however many degrees, it seemed like you had very fine control over the degree of rotation. What mechanism are you using to do that?
Yeah, Hal can tell you all about it, or John students. But when you have two different layers, you're looking at the sharp edges of exfoliated sample, and you're trying to align them by eye. And then you just have to do 10. You have a variety, you measure them. It sounds painful. Wait, I have better news for you. But if you do what's called the homobilayer, you start with a monolayer. This is technique invented by my colleague, Emmanuel Tutok. You tear apart part of it. You move over, now they're perfectly aligned. Now you rotate the bottom piece with a motorized stage. You come down, you have a control of 0.1 degree or even better rotation angle. That's launched the whole area called, twisted-hBN. You have precise control. A lot of fascinating correlated phases emerge in graphene, whole area just enabled by this ability to control the twist angle by 0.1 degree. That's not good enough. They actually want it to be better. Anyway, that's a art still. There's certainly people who are trying to do it robotically. But right now, graduate student has the best touch. So anyhow, so I've been looking for a different platform, partially because I want a different control. I want to control these properties independently. So we come across this platform, I would basically twisting twisted-hBN. I already told you about twisted-hBN. We use it to encapsulate the sample. It's atomically smooth. It's this van der Waals material. You can create an interface that's atomically smooth. And if you sandwich your bilayers between twisted-hBN, the Moiré seem to get more uniform. Everybody get their twisted-hBN from a group, the best quality twisted-hBN from a group in Japan, right? All the group are pushing for the most advanced physical phenomena, get that from them. We do too. One of the things that people have realized is that if you take a bulk crystal, they would have what's called anti-parallel interface. But if you have what's called a parallel interface, you have a chance to develop spontaneous ferroelectricity in this material. And so let me just explain. So this is what's called the parallel interface. So again, there's high symmetry stacking points, right? The A stacking point, the hexagonal is on top of hexagonal. They obey the inversion symmetry. But if you have moved over to a different high symmetry point, now you can see the inversion symmetry is broken, right? So if you, in this, both of AB and BA stacking break the inversion symmetry, And at the twisted interface, you would actually form spontaneous electrical dipole. That HBN is high gap insulator. There's no charge transfer, but there will be slight charge redistribution. This is DFT calculation. You can calculate precisely how big the polarization is and matches our measurement very well. I'll show you that shortly. And interestingly, my student start doing this by folding the layers. You know, tear and stack is very painful. You know, and you don't make many. You know, my students started just blowing nitrogen gun at these layers, and they will fold. When they fold along crystal axes. They either fold along armchair or they fold along zigzag directions, and half of the sample would have ferroelectricity in them. So 50% isn't too bad. So we live with that. And then what I'm going to show you next is a series of measurement that we take using an AFM-based tool, but we use it in a modality called KPFM. What it does is essentially measure the electrostatic potential on the top surface, okay, of this stacked HBN. Okay, so this is the data. People who do transport measurement will be horrified by these spatial gradients. Some are bigger, some are smaller, and they're triangular, not hexagonal, partially because what's called the lattice reconstruction, but I'll spare you that detail just to say you have these superlattice. Also with this twisted HBN, we have a gradient because there's some building strain when we fold them, but it conveniently provide us with an area that we can just do you know, we can measure these supercells and measure a size dependence, right? So we're okay with them as a mechanism study. So I can actually take a line cut. I can measure the surface potential. By the way, the thinner the HBN, the deeper the potential will be because the spontaneous polarization form at the twisted interface. Monolayer, bilayer HBN is really hard to find because they're very transparent, okay? So we didn't bother too much with that. The result I'm gonna show you are all HBN layer with 5 nanometer, 7 nanometer, or even 12 nanometer thick. They're pretty thick by the standards of people working in this field. But the potential trap is 200. As the supercell gets smaller, it becomes, we stop at 50 nanometer. That's how our tool is limited. We don't have the most desirable AFM to do this experiment. And this solid curve is not even a fitting, it's a calculation. And we shifted it vertically to fit into the data point. The idea is very simple. It's actually classical ENM. You have that charge redistribution. You can calculate a polarization based on the integral for the charge redistribution with a Z, that's dipole definition, charge and the separation, right? And then you calculate the potential, you have an exponential function here. Z is the distance to the interface. So you do want to get close to the interface, but what is this G? The G has some constant, but over B, B is the supercell size. If I'm looking at the supercell size about 500 or 100, then my Z, when it changes from 5 nanometer to 7 nanometer, didn't matter too much, okay? So we were able to measure the potential with pretty good accuracy. But this potential is really simple. It's scalar potential. You can also create this potential by doing e-beam lithography. You can gate them, you can create this potential, but now we don't have to fabricate any devices. We can just fold a HBN and give you the surface potential. So what can you do? Another good news is because they're scalar potential, they can add to each other. So this is, we just fold it one more time. If the two interface are same in its twist angle, the potential just simply added to each other. Instead of 200 MeV, we now have 400 MeV with the 3 layers. And then you can extend it. You're not going to do this by hand, obviously. You need to figure out a way to stack multiple layers. Then the surface potential can be as deep as 2 eV. Right? You can trap a lot of things with a potential that's 2 eV deep. But what if the two interface has different twist angle? Then you have this bigger triangle on top of that smaller triangle. The bigger triangle give you potential that's basically flat, and the smaller triangle give you this dominantly sinusoidal pattern. And now you have a ferroelectric material that give you multiple level of ferroelectric potential. So all with HBN just folded or stacked, right? I want to convince you I can actually do something useful with it. So of course I started by looking for a way to impose Moiré potential on a functional layer. What I mean by that is I'm going to take my HBN, and then I'm going to have a functional layer, semiconductor or graphene, bilayer graphene. The electrostatic potential, just like the Coulomb potential between the atoms, will modify the band structure. So now I have a way to impose a Moiré potential on any functional material I put on the top, right? So this is a universal in the sense the potential depth and the period was decided by the HBN. Whatever layer I put on top would experience the same potential, right? Another thing I told you about the potential, how the conduction band and valence band structure in TMD is complicated. But now I put a MOSC2 semiconductor on top, then at each valley, they would experience the same modulation. That's another reason to call them universal potential. If I slide the TMD versus the HBN, I would not see any change. I put a Bernal bilayer graphene. They are not twisted against each other. This is for the expert in the audience. Now I can apply the global gate, actually change the band structure of the bilayer graphene from topological trivial to non-trivial. So there are a lot of things I can do starting with a modulation potential from a substrate. So I can choose really very different functional layer. And I was talking to Oliver this morning and say, okay, you have a ferroelectric material now, put a magnetic on top, magnetic layer on top. Do you have a multiferroic laser material? Not so quick, because you have to make sure they're actually coupled to each other. The electrical polarization may not be coupled to the magnetic polarization. You need to think about that carefully. How do you make that happen? Okay, so now we again start with the simplest thing that we're most familiar with. We put a semiconductor on top, have a monolayer semiconductor, and partially overlapping with a single HBN, partially overlapping with a twisted HBN. On a single HBN, I can see the diffusion of the exciton. On twisted HBN, I no longer can see the diffusion. So that shows you the potential we're localizing the excitons, at least to the resolution I can measure. Okay, it's doing something to the exciton. So we didn't understand what it's really doing to the TMD by the time we published this paper. We were forced to add this data. Reviewer asked for it. We're like, okay, let's put something that we don't quite understand. What we don't understand is we actually see complicated spectrum for the excitons. We just showed you the image, just show you the confinement, but there's a lot more things that's happening. Since then, we understood a little more. Let me also say that right now we're working with large domains. We're not really using the band structure modulation yet. We're not inducing, again, for the expert, flat band physics in the functional layer, but we're working on large domains. We need to improve our process to really use to induce flat band physics in the functional layer. But let me just go with a large domain. So large domain, I've showed you the potential is actually flat, right? Within a large domain, the potential is flat. But between two adjacent domains, there's a quickly changing in-plane electrical field. That in-plane electrical field can actually induce exciton Stark shift because it's pulling the electron hole in different direction. Have an in-plane electrical field would act on positive charge and negative charge in the opposite direction. And I can really see that. This is large domain intentionally. I take optical spectrum within each domain, then they only give me one exciton resonance. But if I take a spectrum overlapping with a domain wall, I actually have additional resonance. That resonance is shifted by the Stark shift. Okay, so what it really does is really the HBN is modulating both the pattern of emission and the spectrum of the emission periodically. Okay, So it followed the period of the Moiré supercell created by the HBN. I don't want to elaborate the detail, but I also want to show you I can combine the ferroelectricity with the light emission properties. So I can actually apply a global gate. I can erase and restore the domain. I can do this over many cycles. And then as I add the electrical field, the spectrum changes. This is a raw spectrum, but if I follow the star shifted peak, I have this funny shaped hysteresis behavior. So this is multi-cycles, multiple cycles of switching monitored by the exciton emission peak shifted. So in this case, I want to convince you that I was actually able to combine the functionality ferroelectricity from the HBN substrate with the light emitting property in the semiconductor. I have an electrical switchable light emitting material in this heterostructure because I have ferroelectricity just by folding the HBN and the light emitting property from the functional layer. I really feel that it's a great platform. Use imagination what you can put on the surface. So for example, there's the Dickey superradiance proposal. Can I look for a collective emission? Personally, I feel like I don't know the requirement of that, how repeatable the emitter needs to be. They're not perfectly repeatable each Moiré cell. But one can maybe think about deposit polar molecule on the HBN substrate. And, and they would orient the dipole of the polar molecule. A molecule have very high quantum efficiencies, can have very high quantum efficiency. Maybe that's a better platform to look for collective emission. So I would mostly end there, and just hopefully you're excited as I am about the HBN as a kind of a universal Moiré platform to put Moiré potential on any functional layer. And I only have one graduate student working on this for the last 2.5 years. We have not done many things on the top, right? We limited people power, students need to sleep, and so we only done semiconductor so far, okay? But you're welcome to join us and use your imagination, your favorite thing you put on top where you want to see a modulation potential. I did promise people that I would talk a little bit about other ongoing project. One of the things I want to tell you is quasicrystals, right? So quasicrystal was discovered in the late 80s by this gentleman. You should search for a YouTube video when he gave a lecture. He was still bitter that many years later because nobody believed him. He's discovered quasicrystals. Those quasicrystal was discovered in a metallic alloy to begin with. And his signature is looking at diffraction pattern like this. Okay. Also, this is a particular material that what is a quasicrystal? Quasicrystal are special atomic arrangement where translational symmetry is broken, but they obey rotational symmetry. And then this discovery, he was given the Nobel Chemistry Prize. I couldn't find many applications of this in chemistry. It was given, I believe, for fundamental conceptual breakthrough, because it forced people to redefine what's a crystal. Right? Crystal was always defined as periodic repeat with translation symmetry, but quasicrystal does not have that, only have rotational symmetry. This is one example. They have 5-fold rotational symmetry. The important thing to realize is that he had a hard job. It was very difficult to convince people because he only had these diffraction patterns, and you actually need to analyze diffraction pattern where the intensity of the diffraction can be 5 orders of magnitude different from adjacent diffraction pattern. You not only need to have really good quality samples, you also need to have really good measurement. Nobody believed him for a long time. He couldn't get his paper published anywhere over 2 years. Eventually, it got accepted. He got a Nobel Prize, But looking at this diffraction pattern and ask, where are the atoms in real space? It's still a challenge. Now we have a chance to study quasicrystal with these twisted bilayers. Most of the work are done with small twist angle, but you can actually have twist them by 30 degrees. We know exactly where atoms are. They're carbon graphene sheets, they're TMD, they're in this hexagonal crystals. If you twist them 30 degrees, You can do this on PowerPoint. You need to, you can go back and check. There's no translational symmetry, but there is a rotational symmetry around it. If you change the twist angle to say something like 21.8, you now have translational symmetry. What's interesting is both of these angles are energetically stable. Chemists can find them in their chamber. They grow them, they either grow in a line way or they form quasicrystals or these minimal period Moiré crystals. Okay? Our colleague find them in STM, using STM because the flakes were very small when CVD grown. They're like tens of nanometer. None of us can find them, but they had atomic resolutions. So they were able to see the local electron density violate translational symmetry, but obey the rotational symmetry. Right? That's what my colleague Kanshi did, but I'll just, because I promised to talk about excited state, I'll just show you that we can actually see signatures of them in optical spectrons. What's special is because this strange atomic alignment in real space. In momentum space, you can actually bring K value and Q value, again, a high symmetry point, to infinite proximity to each other in momentum space, if you consider what's called the high order Umkan scattering. So you have this very special KQ coupling from different layers, and they give us a really rich optical spectrons. They're tunable. You apply the vertical electrical field, shift the bands relative to each other. And at some point, you will see a disappearance of the trion because of localization phenomena. Localization different from Anderson disorder-induced localization, but predictable, just like the quasicrystals. So that's one thing we're working on. We're trying to think about what else we can study on these quasicrystals. They probably have very different thermal conductivity properties. If you use magnetic layer to build them, they probably have different magnetic properties. So again, we're at the early stage of exploring this. And then, I talk about trion, which is a bound electron hole pair. I just want to show you, I'll skip the detail, just show you the special configuration where the electron hole pair may not be sitting at the same location with the doped charge. So you can have this special situation. You can actually you can control the separation between the dope hole and electron hole pair, or between the electron hole within the exciton. So I guess I want to leave you with the thoughts that there's many versatile world of excited state in Moiré systems. There's just a lot to understand. We're limited by our tools at the moment, but there are people who are using very advanced tools, either STM with light axis or ARPAS, where they actually are able to track where the electron holes are in momentum space, or TEM studies, where they really try to pin down where are the electron holes in these Moiré superlattice. And I think with that, I'll end my talk, and thank you very much for your attention.
If you go back to when you were showing the twisted hBN layers, it looked like you mentioned that there's like this spatial gradient, and I was wondering, this is like, at least from my perspective, not being really accustomed to looking at these, it almost, like in the next slide too, it almost looks like it's in perspective. Is that not true? It's like flat, but then it's just the spatial gradient.
Yeah, they're flat.
Okay.
It's probably just a visual effect.
They're flat. This contrast is basically electrostatic potential, the higher potential, lower potential. That's what the contrast is.
How small can you get those? You said that you're just focusing on the larger ones?
Because we couldn't image smaller ones, but if you use the tear and stack method, it's under your control. But how small they can be.
It's larger stacking domains when you get very.
No, actually, if you go beyond 1 point, if you go to larger angle, they're more stable, right? It's dangerous to work with small twist angles because they would gradually relax to perfect alignment.
Very impressive work. One question about difference between gallium arsenide and the TMDs, or one difference that people think there is a strong electron-hole exchange interaction in TMDs.
Yeah.
Did you see any signatures of that?
Yeah, actually, I think the excitons, you can put them in two valleys, right? The valley decay is actually very rapid because of electron-hole exchange interaction. There are also different species of trion because of electron-hole exchange interaction. There are definitely many signatures of that. It's a little technical to get into that. So definitely. So I would say maybe the first 5 to 8 years, all we're doing in TMD is kind of emulating what people are finding in gallium arsenide, except for with different numbers. But with the Moiré, I think we're really in the routine. You can study things that you cannot find in the gallium arsenide systems.
Yeah, so you mentioned earlier that part of the challenge with having control over single excitons and the low rotation regime bilayers is that the lattice sites or the low potential sites are basically too close together.
Yeah.
I'm wondering if the quasi-crystal arrangements that you showed have like a higher chance of being able to resolve single excitons.
So the thing is, I can't actually really picture where we know localization happens. We don't have the tool to probe where are they. They're localized. I don't know the pattern. You ask, I think I finally may find someone who's willing to help us. Typically you ask a DFT person, you said, can you calculate quasi-crystal? And they say, get out of here, right? Because supercell is already too large and quasi-crystal is impossible. But this person at Berkeley, he's actually interested in calculating the quasi-crystal problem because it's a matter of how big of how many atoms you need to calculate to capture that property, right? So the quasi-crystal, the really fundamentally block function, block theorem no longer works. Block theorem rely on this translational symmetry. People do single particle calculation, like, try to, to think about what kind of bands you may have, and they have some success, duplicate what people can measure in bilayer graphene, for example. Bilayer graphene had an earlier try at this quasi-crystal work. But TMD and bilayer graphene offer different things. It's very challenging to really calculate or predict. Excitons is another level up. Many body state, excited states. So you need to find brave young people who are willing to work on these problems.
When are you mostly using emission spectroscopy?
We do use emission and absorption. Yeah, what's the difference is emission is a two-step process. It had to absorb first, and oftentimes they decay to some lower energy states and then emit. For example, I told you about the intralayer exciton, right? The intralayer exciton has very large absorption, 5%, but the interlayer is 20 times weaker than that. So if on a really good, well-prepared sample, you would only see interlayer exciton in luminescence. You will only see, intralayer exciton in absorption. They kind of measure different group of exciton in the material.
Charge transfer.
Yeah.
I think I missed. So it's within a single layer.
Yes.
The three.
That's what we believe. Oftentimes this picture, intralayer exciton per 10 electron in one layer, holding the other layer, that's a simplification.
Yeah.
These layers are 0.3 nanometer thick. The wave function can certainly extend to the other layer. Most of the time, it's a bit of a hybrid. Maybe hole is more delocalized or electron is more delocalized. So you kind of have a funny distribution between the electron hole wave.
How do you know the extra carrier is sort of spatially?
Right, so you kind of monitor how they behave when you apply in a vertical electrical field, right? So that helps you to know where they were initially, right? It depends on the electrical field, how they will move electron hole in a very definite way. You see how your spectrum evolve. That's how you, and of course you can start with a DFT calculation as a guess, right? And then you watch how these resonance evolve with electrical field.
You're describing how to actually construct the Moiré heterostructures with a set twist angle. It seemed like once you do that, it's a very final and set property. Are there any ideas about dynamically controlling the twist angle?
Certainly, people have, okay, so, it's hard to rotate a single layer against a single layer. That's why I also like the HBN. There are people who learn how to make a wheel, like carve out the little driving wheel for the HBN. You can take an AFM and push that wheel. You rotate, you change the size of the supercell. It's pretty cool, yeah. So it's possible to do a dynamic control. Not as dynamic as you want, right? But you need to drive a steering wheel in some way to control that.
Layer sharing mode and have some breathing of the Moiré.
You mean rely on the mechanical properties? And there's also people who are trying to use MEMS devices to dynamically tune them. Yeah, we haven't tried something so advanced yet, but there's certainly ways to. What you really want, you don't want a fixed twist angle, right? You want to be able to change it. But a lot of people also thinking about changing the property using strain. That can be a little more dynamic.
All right, well, let's thank Elaine.